Hello everyone, I am Rahul Mandal US and 1V20CS124, and today in this video I am going to discuss four topics that are IV and PV characteristics of solar panel, types of solar cell material, working of solar cell, and heliostatic concentrators. So here is a diagram for IV and PV characteristics of solar panel. Now let's see the IV characteristics. So the IV curve represents the current and the voltage relationship of a solar panel. The current is proportional to the amount of sunlight hitting the panel. The voltage is proportional to the number of cells in the panel and the material used to make the cells. The IV curve of solar panel is affected by factors such as temperature, shading, and the angle at which the panel is mounted. Now let's see the PV characteristics. The PV curve represents the power that is represented by P and the voltage V relationship of a solar panel. The maximum power point, that is MPP, on the PV curve is the combination of voltage and current that produces the maximum power output from the panel. The MPP varies depending upon the amount of sunlight hitting the panel, the temperature and the load on the panel. The efficiency of a solar panel is the ratio of the power output to the power input, and it is affected by the PV curve. Now we will see types of solar cell material. So there are several types of solar cell materials such as monocrystalline silicon, polycrystalline silicon, amorphous silicon, cadmium telluride, and copper indium gallium selenide. Each type of each type has its own advantage and disadvantages. Now we will see the working of a solar cell. So it depends upon various effects. So first we will see photovoltaic effect. The basic principle of a solar cell is the photovoltaic effect, which is the ability of certain materials to convert light energy into electrical energy. The photovoltaic effect is caused by the absorption of photons, that is, particles of light, by the solar cell material, which creates an electric current. The second topic is p-n junctions. Most solar cells are made from p-n junction, which is a junction between two types of semiconductors with different doping levels. The p-n junction creates an electric field that separates the electrons and holes generated by the absorption of light, which results in the generation of a voltage. Third is energy bands. The energy levels of electron in a semiconductor material are arranged in energy bands, which are separated by band gaps. When a photon is absorbed by the semiconductor material, it excites an electron from the valence band to the conduction band, creating an electron hole pair. Fourth one is electrical contacts. Electrical contacts are placed on the top and bottom of a solar cell to allow the generated electricity to be extracted. The top contact is usually a transparent conductive material, such as indium thin oxide, which allows light to pass through. The bottom contact is usually made with a metal such as aluminium or silver, which provides a low resistance path for the current to flow. Now we will see heliostat concentrators in detail. So what are heliostatic concentrators? Concentrators are devices used in solar energy systems to concentrate sunlight onto a smaller area, which can increase the efficiency of energy generation. Here is a detailed explanation of how heliostatic concentrator works. So first we will see what are heliostats. Heliostats are mirrors that are mounted on motorized trackers, which can rotate the mirror to follow a sun's path throughout the day. Heliostats are usually arranged in a field with each heliostat reflecting sunlight onto a central receiver. Second are concentrators. The central receiver is surrounded by a concentrator, which is a structure that focuses the reflected sunlight onto a smaller area. The concentrator may be a parabolic dish, a fluorescence lens, or another type of reflective or refractive element. Third is thermal energy. When the concentrated sunlight hits the central receiver, it heats up the fluid such as water or heat transfer fluid, which is circulating through the receiver. The heat fluid can then be used to generate steam, which drives a turbine to generate electricity. Now we'll see the advantages of using heliostat concentrators. Heliostat concentrators can achieve higher temperature and therefore higher energy densities than flat plate solar collectors. Heliostat concentrators can also be used in conjunction with thermal storage systems, which allow the generated energy to be stored for later use. Heliostat concentrators can be used in a variety of applications, from a small scale heating and cooling system to a large scale power plants. Now we will see some challenges faced by heliostatic concentrators. Heliostat concentrators require a large amount of space and clear line of sight to the sun. Heliostat concentrators are also more complex and expensive than flat plate solar collectors. Also, maintenance and alignment of the heliostat and concentrators can be challenging.